Welcome. In today's video, we're going to derive the moment generating function of the Poisson distribution. We're also going to use this moment generating function to derive the first moment, the second moment, and the variance of the Poisson distribution. So let's begin. Firstly, let's just remember or recall what the probability mass function of the Poisson distribution is as a bit of a reminder. So remember, if x is distributed as a Poisson distribution with rate parameter lambda, then the PMF of x is given by the following. So it's px of x, and it's given by e to the negative lambda to the x all over x factorial. And remember, this is valid for these particular values of x, or in particular, x can take values 1, 0, 1, 2, and so on and so forth, all the way up to infinity. So, using this particular function here, we can now compute the moment generating function. So the MGF of x is, so recall, we have m subscript x of t, it's a function of t, and we define it, of course, as the expected value of te to the power of tx. And in the case of a discrete random variable, which the Poisson distribution is, we can use the formula, the sum across all x values of e to the tx px of x. That's our generic definition. Now what we can do is we're going to substitute in two parts. Firstly, what we're going to do is we're going to substitute in the sample space of x, and then we're also going to substitute in what px of x is. So firstly, using the summation, what are the possible values of x? It's across all x, or quite simply here, we can say x equals 0 all the way to infinity. We've got our e to the tx here, and then we can also substitute in our e to the negative lambda to the x, all over x factorial. It's looking a little complicated, so let's see if we can simplify it a little bit down. So the first thing I'm going to do is, I notice this is from x to infinity, so we've got our variable x here. So anything that's not dependent on x, in particular this e to the negative lambda, I'm going to take outside the summation as a constant effectively. So I can take that e to the negative lambda, sum of x equals 0 to infinity, of e to the tx lambda to the x, and then of course all over x factorial. We can do a bit of further simplification. Notice here we have e to the tx, and then we have lambda to the x. So quite simply, using our power laws, I'm going to rewrite this whole expression here into the lambda. So using our power laws, what we can do is we can bring the lambda e to the t, and we can take this all to the power of x. And we've got this here, x factorial. Now, what's interesting here is this particular expression, because one of the interesting aspects of, well, this expression should look familiar to you in some sense. Well, maybe it won't look exactly familiar to you, but if I, for example, rewrote this as e to the negative lambda, and I go x equals 0 to infinity. Now, I'm just going to write this as a to the x over x factorial. And I'm just going to put a side note here. A is equal to lambda e to the t. So I've just got some expression for lambda. Now, perhaps this might look a little bit more familiar to you. This summation sign actually ends up being the Taylor approximation, or actually it's not just an approximation, it is the polynomial expression that we use to calculate, or it's the polynomial expression for e to the power of a. So here we can actually write this now as e to the power of a, and that's something hopefully you can recognize. If not, perhaps review your Taylor expansions of e to the power of x. But now that we know that this is e to the power of a, we can rewrite this a bit more. Just our expression here, this becomes e to the power of negative lambda, that's still there. Now I'm going to replace our a with lambda e to the t in here. So again, let's go to a new page. Let's just refresh our memory. So we had mx of t is equal to e to the negative lambda e to the lambda e to the t. We're going to combine our expression together. So we know from our power laws, when you have something or a base to the power of something times that same base to the power of something, it's the equivalent of adding the exponents. So we can now write this as e to the lambda et minus lambda. And we're going to do one more step here. This is all up in the exponent. We're going to factor out lambda. So we go e to the lambda, e to the t minus 1. And that is the moment generating function for the Poisson distribution. Now, note here that in this case, we can also write it in this form here, you might see. And it's just perhaps a nicer form to write it in. This exp at the front here is the equivalent of taking e to the power. Sometimes it's written like this simply because sometimes it can get a little bit small, the writing, when you've got e to the power of and then e to the power in the power itself. So sometimes we can write it like this. However, for simplicity's sake, I'm going to just stick with this. I think it might be easier to show you. So now that we've derived the moment generating function, and before I go on, I should point out that this moment generating function is true for all values of t. So could point here, t is an element of R. There's no restrictions, in other words, on t for this to be true. In particular, we know that from the fact that for this particular value of a, no matter what the value of t, in other words, no matter what the value of a, this particular series will converge to the exponential distribution. So we don't actually have to place any restrictions on t in this instance. So, now that we've covered that, what we can do here is we can compute the first and second derivative of the moment generating function, and that will allow us to compute the first and second derivative of the moment generating function will allow us to compute the first and second moment of the distribution. So let's start with taking the derivative. So mx of t prime is equal to the derivative d dt of e to the lambda e to the t minus 1 So how does this work? Well, in this particular instance, what we have is we have an expression for t at the top here. So we know that the derivative of the exponential is simply equal to the exponential, but then we have to multiply what is inside the brackets of the exponential. So we've got e to the t minus 1, sorry, the power, we take the derivative of the power inside. And then, of course, this expression stays the same, e to the t minus 1. Now, here it becomes a little bit more tricky, or not really tricky, actually. It's quite a simple expression. It's a constant times e to the t. So we know when you differentiate a constant times e to the t, that just becomes lambda e to the t, and the lambda and the negative 1 there are a constant with respect to t, so it just differentiates to 0. So then putting this all together here, again you have a power, and this might be a little bit tricky, but we'll try to get through it. What happens here is we have a lambda out the front. We have an e to the lambda e to the t minus 1. And then notice here we have an e to the t. So we've got to add this to our expression at the top here. So in fact, it becomes a plus t. And so this is an alright expression to deal with. However, computing the second moment might be a little bit more challenging. So it's a bit ugly at this stage, but let's see if we can compute the second derivative. So mx double prime of t is equal to d on dt of mx prime of t. In other words, the second derivative is the derivative of the first derivative. We're going to stick in our expression for the second derivative, the first derivative. So we've got lambda e to the lambda e to the t minus 1 plus t. Bit complicated, but then recall again that when we have a derivative of an exponential, what we are left with is first we have the original exponential minus 1 plus t, and then what we also have is we need to multiply by whatever's in the power. So again, that becomes lambda e to the t minus 1 plus t. And of course, that constant out the front can just also become a constant out the front by the rules of differentiation. So let me again take this expression. Let me take this expression, copy it across. Copy that, and we'll go to the next piece of paper. Let me paste that here. So again, this is our second derivative, double prime t. We're going to do a little bit of simplification. So this becomes lambda e to the lambda e to the t minus 1 plus t. And then in this expression here, when we differentiate with respect to t in the exponent, again, that just becomes lambda e to the t, because there's a constant times e to the t. That just becomes lambda e to the t. And then, of course, we also have this plus t at the end. And when you differentiate t with respect to t, you end up with plus 1. And so this is our expression for the second derivative. So now we can compute the moments, or at least attempt to compute those moments. So the first thing we note is that we've got e to the power, or the expected value of x, by definition is the first derivative of the moment generating function evaluated at t is equal to 0. So we're going to take that expression for the moment generating function that we had here. Here it is nice down the bottom. I'm going to try and copy that across here, paste that. Seem to have picked up a few extra bits and pieces that I didn't want. But that's okay. So here's our expression here for the first moment. And we need to evaluate that at t is equal to 0. So let's just plug that in right now. E to the lambda, and then e to the 0 minus 1 plus 0. So far, so good. Now that becomes lambda e to the lambda, e to the power of 0 is just 1, minus 1 plus 0 we don't need anymore. This whole expression becomes 0 at the top because 1 minus 1 is 0. And so then e to the 0, this whole expression here becomes e to the 0, and e to the 0 is simply 1. So all we're left with is quite simply lambda. Quite nice simplification there. Let's see if we can get something sort of similar for our e to the power of x squared. Hopefully it will also simplify. So again, the second moment of x is given by the second derivative of the moment generating function evaluated at 0, and we have our expression for the moment generating function at the top there. I'm just going to copy, I'm going to hand copy given all the technical difficulties I've had. And then we're going to put that through, and then that is evaluated at t is equal to 0. So now here what we can do is we can plug in a value of t, so that becomes lambda e to the lambda e to the power of 0 minus 1 plus 0. Then we've got our lambda e to the 0 plus 1. And now we can start doing our simplification. So this becomes lambda e to the, again here, e to the 0 is just 1, sort of similar expression. This will all end up becoming 0, because you got 1 here, minus 1, so that all cancels out to be 0. You got plus 0, so we've got e to the 0 here. Then we've got multiplied by lambda, because e to the 0 again is just 1, and then we've got plus 1, and then if we expand this a little further, that becomes lambda squared, and that lambda squared comes from the fact that you've got that first multiple, lambda to the lambda, and then we've got lambda plus 1 here at the back, so it just becomes plus lambda. And of course, remember that e to the 0 is just 1, so I've sort of ignored it. Finally there, we can calculate the variance of x, and again, the variance of x is equal to the expected value of x squared minus the expected value of x all squared, which in this case becomes, in our expression, lambda squared plus lambda minus, and then we have our expression up here all the way at the top for lambda at the top there. So we just need to plug that into our x squared, and so that becomes lambda squared, and then after all of that we get back to lambda. And this does match up with what we expected, because we know that the variance and the expectation of a Poisson distribution happens to be its rate parameter. Thanks for watching. Looking forward to seeing you in the next video.